Hey, welcome. Today, we're going to pull back the curtain on this silent, invisible battle that's happening all around us. You see it on boats, on bridges, maybe even in your own backyard. We are talking about galvanic corrosion, this hidden force that can literally eat metal away. So you've probably seen something like this, right? You've got this perfectly fine piece of metal, but right where a different kind of bolt is attached, there's this really aggressive rust and decay. It's not random at all, it's super targeted. So what's going on here? Why does one metal seem to just destroy another one just by touching it?
All right, let's dive into our first section, an everyday mystery. Now, this is not a new problem. Engineers, sailors, they've been wrestling with this for centuries, and figuring out the why is really the first step to building things that actually last.
Okay, first things first. This is not just your garden variety rust. Rust is just what happens when iron meets air and water. Galvanic corrosion, though, that's totally different. You've got to think of it as an electrical process, a tiny invisible war that's happening between two different metals. So that brings us to section 2, the 3 key ingredients. Just like any recipe, this whole process needs a few key things to get started. You need all 3 for the corrosion to kick off, and here's the good news, if you can take away just one of those ingredients, you can stop it dead in its tracks. The absolute best way to picture this is to think of it as a tiny, unintentional battery. But, instead of powering your TV remote, this battery's only job is to dissolve one of the metals it's made from. It's a really destructive little thing. So here they are, our 3 ingredients. First, you need 2 different types of metal. These are the opponents in our little battle. Second, they have to be touching, creating an electrical path between them. And third, you need an electrolyte. Think of the electrolyte as the battlefield where the chemical reaction actually goes down.
So what on earth is an electrolyte? I know, it sounds super complicated, but it's really not. It's just any liquid that can conduct a little bit of electricity. The most famous one, of course, is salt water, which is exactly why galvanic corrosion is such a massive problem for ships. But it can also be something like acid rain or, heck, even just the humidity in the air, creating a super thin film of moisture.
Okay, moving on to section 3, the metal pecking order. So you've got your 2 metals, you've got your electrolyte, but which one of them actually corrodes? Well, it is not random at all. It's all decided by something you could call a metal pecking order.
To put it really simply, in the world of metals, some are kind of chemical bullies, and some are victims. And when you put them together in that electrolyte, one of them will always get protected, while the other one is forced to corrode. Every time.
This chart here is called the Galvanic series, and you can just think of it like a power ranking for metals. Metals at the top, like gold, are called noble. They're super stable and they resist corrosion. They become the protected one, the cathode. Then you've got the metals down at the bottom, like zinc. They're less noble. They're way more reactive, and they become the anode, and that's the one that gets eaten away.
And here's what that looks like in the real world. Let's say you use copper screws on a steel plate. Well, you look at the chart, steel is less noble than copper, so the steel corrodes like crazy to protect the copper. A very bad match. But if you use zinc-coated screws on that same steel plate, zinc is even less noble than steel, so the zinc sacrifices itself to protect the steel. Now that's a good match.
This brings us to the most important part. Section 4, how to stop the rot. Now that we actually understand the problem, we can get into all the clever ways that engineers have figured out how to solve it.
So the question becomes, if this whole galvanic corrosion thing is really just a tiny electrical circuit, how do you break it? Well, remember our 3 ingredients? The solution is all about taking one of them out of the picture.
So here's the prevention playbook. First, you can isolate the metals. Use something that doesn't conduct electricity, like a simple plastic or rubber washer, and that breaks the electrical path. Easy. Second, you can try to remove the electrolyte. Basically keep the parts as dry and clean as possible. Third, you can choose your metals wisely. Pick ones that are really close together on that galvanic series, which makes a reaction way less likely. Or, and this is the really clever one, you can add a defender.
This all leads to a classic saying you hear in the maritime world, to save the ship, sacrifice the zinc. And it just perfectly captures the most ingenious solution of them all, sacrificial protection. This right here is a sacrificial anode. What you do is you take a block of a very less noble metal like zinc, and you bolt it directly to the steel hull of a ship. Now, because zinc is so much lower on the galvanic series, it becomes the anode for the entire ship. The saltwater electrolyte then attacks that zinc block, which corrodes away over time, literally sacrificing itself to protect the much more important steel hull. It's brilliant.
So when you get right down to it, galvanic corrosion isn't just some random decay. It's a predictable process that follows very clear rules. And once you understand those rules, once you understand the battle, you actually gain the power to control the outcome and choose the winner.
And that kind of leaves us with a final thought. Now that you know what to look for, those 3 ingredients and the pecking order of metals, what unseen metal battles are happening all around you? I mean, on your car, your bike, the pipes in your house? This war is happening everywhere, but now you know how it all works. Thanks for tuning in.